Hello, everybody, and welcome to science class today. I am glad that you're here. Make sure that you have your science journals out. Remember, I do require students to take notes on lessons. I think that the ability to take notes and writing down the important terms of the day will help us remember things better, and it will prepare you for college. So today, your goals are to write down compression wave, transverse wave, crest, trough, rest position or equilibrium, amplitude, wavelength or cycle, period, time and distance, and be able to label those in a diagram. Now this recording will go through those quickly, so just know that any point in time you need to hit pause, please do, and write those in your science journal. Now remember, there's two ways to get notes in your science journal. You can open Word, and you can take screenshots by pushing Alt and print screen at the same time and hitting Control V, paste into the Word files, and you can grab them that way, or you can use the old-fashioned method, which is getting out your pen and a notebook and writing it on a piece of paper. So, good review. Let's go on. Today we're going to be talking about Utah Standard 2.4, and 2.4 is a cool standard because it's about physics and it's talking about how energy moves, and energy is unpredictable. And that's why in our engagement lesson I asked you guys to look at two recordings of a Slinky and a Newton's cradle. So two favorite toys that people like to look at and play with. Now if this sounds like brand new information to you, you need to stop the recording right now, go back into your online school, and finish that engagement cycle before you continue. And the reason why is playing with those toys will answer to the question of why do we need to learn this? So go back and get that done first. All right, so Utah Standard 2.4 says to use computational thinking to describe a simple model for waves that shows the pattern of wave amplitude and being related to wave energy, emphasize describing waves, which is why we have to learn the terms, and both quantitative and qualitative thinking. Examples that we're going to work through today could be graphs, charts, computer simulations, which is what's going to be at the end of our instructional cycle, our homework, a physical model, or demonstrations of amplitude and energy correlation. Now those sound like really big words, and that's because science has to use common language to explain what you already know. And that's why I brought my Slinky toy to class today. Woohoo! And that's why I had you guys start out with our engagement cycle as looking at two favorite toys that everybody likes to play with, the Slinky and the Newton's cradle. So here we go. All right, so phenomenon-based learning. The reason why the Slinky and the Newton's cradle move in ways that is not predictable is because they are what's called a medium. Alright, it doesn't mean that's the size of the toy. Medium means an object or a substance that has matter that energy can move through. That's why you can bong this side of the Newton's cradle and whack it this way, and only one ball will move out the other side. Kind of crazy, but that's why everybody loves it and wants to play with it. Okay, so how do we describe these things? First thing we have is an S wave that makes a kind of an S shape. Let's see, I can put this in the webcam. You see how my Slinky is bending? That a bending Slinky like this makes like an S is called a transverse wave. It means the medium, in this case the coils of the Slinky, are displaced perpendicular to the energy's direction of motion, which means it makes this arc up, down, up, down. Or it makes a nice little bend like this. And if you're like my daughter, you're going to take this and you're going to make it arc over. Sorry, I'm trying to get this in the webcam. And it will bend over and walk all the way down the stairs. Pretty cool trick, right? Everybody loves that one. All right, so if you got a Slinky, you can go ahead and pause the video, grab it, and see if you can make your Slinky walk end over end and go down the stairs. All right. So quickly, we're going to have a little bit of a brainstorm moment. 15 seconds in your science journal. I want you to brainstorm what types of scientific phenomenon can you think of would make an S-curve type of wave. And I want you to write them in the science journal because I want you to link the stuff that you already know, because you guys are super smart, to the ideas and the term transverse wave. So 15 seconds, ready, set, go, 15, 10, And here we go. 5, 4, 3, 2, 1. Now here's the deal. If that just went too fast for you and you couldn't hurry and write something down, that's okay. You guys can hit pause. So go ahead and hit pause, get some ideas written down, and then I'm going to show you my ideas. All right, so here are some of my favorite examples of a transverse wave. If you look closely, we have a violin, and look at that string. The string is the medium, and it is making our nice little arc path that you can create with the slinky. Kind of cool, huh? Here we've got a nice little calm area of water, and we bloop, put one little drop in it, and it sent out a series of waves going out. And then another one that's really super useful is light and electricity. And basically we call those kinds electromagnetic waves, which is a big fancy term, which means a whole bunch of atoms moving, mostly electrons. And when we take and shoot light at a prism, it bends and it arcs out, and it actually bends the light into different frequencies. And so when it does that, we could have a really, really compressed blend. You see, like my slinkies all connect together, or we can have a really, really stretched out bend, and that actually changes the colors that we see. So it's a really big deal, and transverse waves are really helpful. Okay, the next type of wave is what's called a compression wave. A compression wave is, you can think of our slinky stretching out and impacting, stretching out and coming back in. Or you can think of your hands clapping, all right? You can do the happy dance, the clap dance right now. It's moving like an accordion, okay? We also call this a longitudinal wave. So you can think of it as the wave is going long, okay? So you've got the slinky going long across my face, and then I send one pulse of energy down it. You can see that it gets thin, it gets stretches in and out, in and out, in and out. And so we call it have areas of compression and refraction, okay? So here are some of my favorite examples of a longitudinal or transverse wave, and I want you to brainstorm some of your own. So one of the coolest ones is that air moves this way, and because air moves, stretches out and compresses back and forth, guess what? That makes it so we can hear things, and that's how I have sound. My voice is causing a vibration of air to compress and stretch, compare and stress. It goes to my mic, and that's why you can hear me talk. Another thing that's really cool is earthquakes. The ground will stretch, which is why you see a crack, and then it will smush back in, and that's why the road popped up. So earthquakes are compression or longitudinal waves. Pretty cool, huh? Okay, so brainstorm for a second. I want you to connect this word phrase compression wave to something you already know. So write down an idea. 15 seconds to brainstorm. What is a phenomenon of compression wave that you could think of? You can think of instruments. A lot of them uses this, especially any kind of instrument that vibrates using sound like a trumpet or an accordion. So 15 seconds, here we go. 15, 10, and we go 5, 4, 3, 2, and 1. And if you need more time, you can please hit pause right now. All right, so good. You've got an idea and a connection made of what is a compressional wave. So our goal for the rest of class is to be able to label these points on a diagram. So we have crest at the top, trough at the bottom, amplitude, and wavelength. So let's go through and get these definitions for our science journal. If you need to hit pause while you're taking a screenshot or hit pause to write in your science journal, please do at every slide. So crest is the highest point of the wave, and yes, this is a crest, and this is a crest, and this is a crest, and there will be another one over here if it kept on going. Crest is always the top. So think of yourself hiking, and you're hiking to the top or the crest of the mountain. You've got that. Good. Okay. So hit pause if you need more time. Next one is trough. Trough is the bottom of the wave. And I actually have 3 horses, and they like to stick their heads in the trough to get a drink. So their head always goes down. So now you can remember the trough is always at the bottom. Okay. This is a trough, and this is a trough. And this over here, my screen, my faces are hiding, is another trough. Good. All right, rest equilibrium is this flat line right through here. It's where the medium would be without any kinetic energy going through it. Okay, so what that would mean is you've got my slinky here, and if I just hold it flat right here, there is no energy going through it. I can hold it sideways. See, look, it's all just a bunch of coils stuck together. No energy is going. But if I move it, I suddenly made energy go, and it made an arc pattern, and you can see that now gravity is making it form a trough. Conversely, I can flip it up, and now it's formed a crest. Okay, so rest equilibrium is no energy moving through it. You could also think of a nice cool lake, and you put one drop of water. It's nice and cool and still before the water hits there. That water is at rest position or equilibrium. Amplitude is the maximum height above the rest position. So this one's an easy one to remember. You sleep all night and you go to rest. When you get up in the morning, you better brush with crest, right? You need to brush your teeth when you get up in the morning. So you guys can always remember, every morning when you get up, you're going to go from rest to crest. So amplitude is rest to crest. And so we can actually measure how high this arc is in any type of wave, or how low too. So that's a kind of a cool thing. And you will be doing that on your virtual lab. Wavelength is the distance from crest to crest or trough to trough. And this change of wavelength changes frequency. So you might hear things higher, might hear things lower. That wavelength changes. All right? And last but not least, we can actually time these things out. A period is the amount of time for the wave to actually repeat itself. So if you need to get these done, I sure hope you hit pause and got these definitions down. Otherwise, you can just drag the slider back and click on and go get screenshots of these definitions that you need. Also, I've also put a link to our textbook, and you can also get them from there as well. So moving on. To-do list for the rest of the lesson. I want to make sure that you wrote down in your discussion post a hypothesis of Slinky and Newton's cradle. And remember that you have to answer to other people's discussion posts, so we get a chance to visit with everybody in class. Next thing is, after this recording, there is a quiz in our online school. You need to take it because I want to see if you understood what I just taught you. Next, you're going to have a worksheet about the PhET wave computer simulation. You're going, wait a minute, what is that? And run the PhET computer simulation. I've never done a computer simulated lab before. Let me show you. This is what it looks like. We're going to run this called Waves on a String. Hang on, I've got it running. When you load it, it's going to look just like this. And what you're going to see in online school is you think it's a picture. It's not. Click on the wrench and it will move. Click on oscillate and it will spin. And you can change fixed end, loose end, no end. You can change everything how it works. You can even change it so it's a pulse and you have to click on it and it will pump down. For your lab, you will have to get the rulers out. Rulers are right here. And you'll have to measure this. If you need more instructions, there is an embedded video on the online middle school. Okay, so let's finish up class real quick. Go back to my presentation. So last but not least, I'm glad you're here today, and I'd like to end with the joke of the day. Joke of the day today is about matter. And we know about matter's important in physics and chemistry, and this one's joke says, along with antimatter, we have discovered dark matter, and the recent existence from students is doesn't matter, which appears to have no effect on the universe whatsoever. Haha, good joke. So go ahead and make today amazing. You guys have a great day.